Hello, welcome to my video lab report where I'll be presenting the analysis of a 2D spring mass system. Let's begin. We're analyzing a spring mass system that moves in both the X and Y direction. Our goal is to model the system's motion and compare it with real-life data extracted from a video. The key result is our model does a good job predicting the motion and the energy is conserved. The model applies Newton's second law and calculates forces using Hooke's law. Energy forms kinetic, gravitational, and spring potential are tracked to confirm conservation. These are core principles from the foundation of our predictions. This graph shows how energy changes over time. The orange line is total energy, and as you can see, it stays constant, proving that the system is conserving energy. The oscillating forms show energy being transferred between types: kinetic, gravitational, and spring potential. Here's the X position over time. The red line is the experimental data, and the blue line is our model. You can see that they're generally aligned, with small differences that could come from measurement noise or limitations of our model. This graph shows the Y position. Again, our model tracks the general motion well, though the experimental data has some jitter. This is because of the video resolution, calibration, or frame capture rate. This slide covers the setup and what assumptions we made. We used data from the video to determine initial position and velocity. The spring constant and the mass are reused from previous labs, and we take a small time to improve numerical accuracy in our model. This is a frame from the model output. It shows the spring and mass moving through the space as predicted by the code. It matches the general motion seen in the video. The code runs by updating the force at each step and applying it to get new velocity and position. It uses a small delta t, assumes an ideal spring, and includes 2D force calculations. We use the tracker data to estimate how long each oscillation takes in both directions. The periods match closely, which shows the system's motion is consistent and our model is working well. When comparing the graphs, the trends are clearly similar. Some mismatch is expected because real-life data is noisy and our model doesn't include all possible effects like drag, but the physics checks out. There's always errors in experiments. In this case, the main ones are from video tracking and assumptions in the model, like ignoring air drag. Even so, the matchup is quite good. This lab shows that with some basic physics and coding, we can model complex motion, and since energy stays constant, it means our model is doing a good job following real physics laws. To conclude, this lab showed us how physics and code come together to describe motion accurately. It's a great example of real-world systems obeying the same laws we learn in class.